Let's talk about something that's right at the edge of AI research. How do we get our large language models to actually listen? I'm not talking about just slapping a text-to-speech voice on top of a chatbot. I mean, how do we teach an AI to understand raw audio, the sound itself?
I mean, you've probably noticed this, right? Why do our voice assistants, even the fanciest ones, still sound kinda flat? And more importantly, why do they totally miss the point when you're being sarcastic or excited or frustrated? Well, it's because most of them aren't really listening. They're just transcribing your words to text, thinking in text, and then reading a text answer back to you. They don't get the feeling because they never even process it.
And the root of the problem, it all comes down to this one massive number, 16,000. That's how many individual data points or samples are packed into a single second of audio. Just 1 second. Compare that to text, where a second of speech might be what, 3 or 4 words? This incredible density is the huge technical wall we've been trying to climb.
All right, so here's our game plan for this explainer. First, we're going to unpack why speech-based LLMs are playing catch-up to the text models. Then we'll get into the secret sauce, how to compress all that sound into manageable little tokens. After that, we'll look at a huge breakthrough with a codec called MIMI and a really important trade-off that comes with it. And finally, we'll zoom out and see what's next for the future of audio AI.
So you might be thinking, why not just feed all those audio samples directly into a giant transformer model, like we do with text tokens? It seems like the obvious first step, right? Just try to predict the audio one sample at a time.
And this is where the scale of the problem just becomes completely insane. With a text model, a context window of about 2,000 tokens can hold whole paragraphs. It gets the story, the meaning. But for raw audio, that same 2,000 token window, where each token is just one of those tiny samples, covers only 128 milliseconds of sound. That's not even a full syllable. The model has zero chance of figuring out what's going on.
So what do you get when you try this? Well, the researchers who wrote the article put it best. You get babbling sounds and, my personal favorite, nightmare fuel screeches. It's just noise. And if that wasn't bad enough, it's also unbelievably slow. We're talking half an hour on a high-end GPU just to generate 10 seconds of that screeching. It's a total non-starter.
Okay, so if predicting sample by sample is a dead end, what's the move? The answer, the whole key to this, is compression. We have to find a way to squish those thousands of samples into a much smaller, much smarter sequence of tokens that an LLM can actually make sense of.
And this is where the hero of our story comes in, the neural audio codec. You can think of it as a super intelligent tokenizer just for sound. It's actually a pair of AI models. You have an encoder that listens to the raw audio and compresses it into a handful of discrete tokens. Then, the LLM does its thinking with those tokens. And finally, a decoder takes the LLM's output tokens and rebuilds the sound wave. Pretty neat, right?
Now, this tech didn't just appear out of nowhere. It evolved through a few really clever steps. It all started with autoencoders, an AI that learns to squish something down, like an image, and then build it back up. The next leap was the VQ-VAE, which made it work for LLMs by quantizing the compressed version, basically snapping it to a predefined library of tokens. But the real magic trick is something called Residual Vector Quantization, or RVQ. With this, you compress the audio once, but then you take the stuff that got lost in the compression, the error, and you compress that too. You can keep stacking these layers to add more and more detail back in.
Okay, so this brings us to a state-of-the-art production-grade codec from a lab called Qt. It's named MIMI, and it takes all these ideas and adds one more brilliant twist that changes everything.
And here's the breakthrough. MIMI splits the audio into 2 different kinds of tokens. You've got acoustic tokens, which describe how something is said, the sound of the voice, the pitch, the speed, the emotion. And then you have semantic tokens, which only care about what is said. The actual words, the core meaning, completely stripped of the speaker's vocal identity. This lets the LLM focus purely on the content, which is what it's good at.
And this separation is seriously powerful. Get this. The researchers ran an experiment where they took an audio clip, threw away all the acoustic tokens, and kept only the semantic ones. Then they let the model dream up brand new acoustic tokens to go with them. The result? As this quote puts it perfectly, the voice is completely different, but it's saying the same thing. That proves it. The meaning is baked right into those semantic tokens, totally separate from the voice.
Now, this whole setup isn't just a magic box you turn on. It actually forces developers to make a really important choice, a practical trade-off between the meaning of the words and the quality of the sound.
Okay, so here's the deal. If you use really high compression, meaning you use fewer of those RVQ layers we talked about, you're forcing the model to only keep the most important stuff, which is usually the meaning of the words. This gives you better semantic understanding. But if you use low compression with lots of layers, you capture all those little acoustic details, which gives you much crisper, higher fidelity audio. So it's a constant balancing act between getting the meaning right and making it sound good.
So we've gone through the core technology, but let's zoom out. Why does any of this actually matter in the real world? And what are the big challenges still ahead for audio AI?
This stuff has huge practical implications. If you're a developer, it means you have to think in this audio to codec to LLM to decode pipeline. For product people, separating the what from the how opens the door to amazing features like real-time voice cloning or deep personalization. But for user experience, it's a big reminder. Even these amazing models still kind of suck at getting human nuance. And really, this whole pattern, embed, quantize, decode, is a fundamental concept you're going to see everywhere in AI, not just audio.
And despite all this amazing progress, there's still a huge mysterious problem called the modality gap. Check out this wild example from the article. Someone asks an audio LLM, am I speaking in a high voice or a low voice, while actually using a super high-pitched voice? The model's answer? It has no idea. It understands the words in the question, but it's completely deaf to the actual acoustic properties of the voice asking it.
But you know what? This gap isn't a failure, it's an opportunity. As the author puts it, this unsolved mystery is exactly what makes audio machine learning such an incredibly exciting field to be in right now. It means there are still huge discoveries just waiting around the corner.
Which leaves us with the one big question hanging over everything. We've figured out how to compress sound and feed it to an AI. But will we ever close that final gap? Will a machine ever understand the joy, the anger, the sarcasm in a voice with the same depth that it now understands grammar and syntax in text? Well, that's the grand challenge that will define the future of AI.